All right. Good morning, everybody. Or I don't know in which time zone you're watching this video in. Today, I'll be covering the second part. This will be the second video in a three-video series of regarding systems. Today, I'll be talking about the types of systems, how systems are further classified into more types. Let's continue. All right. Systems have certain types: open, closed, and isolated. Let's look into it. Firstly, beginning with the open systems. Well, essentially, open systems are systems which have no boundaries regarding energy input or matter input, and the same goes with output. Now, what I mean by that is we can put whatever energy and matter we want to in that system without any restrictions, and that energy and matter can come out of that system without any restrictions. A very simple example of this is boiling water without the lid, right? So the energy input is this flame which goes here. Let me just use this uh, laser pointer. The flame is the energy input which goes into the system, which is the um, uh, kettle with the boiling water. So the flame is the input energy. Energy is being transferred here, and this gets heated, and soon they reach boiling point, and then they reach their boiling point, and then they start evaporating. Some of the water starts evaporating. So that is the matter exchange. So matter goes out of the system, and water was not always present inside the system. So there was an input of water inside the system before the energy input. So that is another input of energy matter. And another input of matter I can tell you is that the output of matter is when the flame keeps boiling the water, and when it reaches its evaporating point or boiling point, it starts to evaporate. And if you happen to put a lid on top of if you happen to put a lid like here at this place, you would see that on the underside of the lid, water starts to condense due to the change in temperature, due to the lid being much colder than the hot evaporated water. They condense into water back again, and then they can fall back into this system. So you see how the energy, how you saw how the matter is inputted and outputted. So input became this water here, this already present water. This was the input. I must correct myself. I think I called this output. That is incorrect. This is the input which is already present here. However, when we put a lid on top of this system, we see that the water condenses and falls back into this system, similar to the water cycle, which we will explore in these examples. And if you see the heat can also leak out from these sides, these two sides of the kettle, through conduction, because alloys usually conduct heat very well. The alloys we use for cooking, and the heat can be exchanged with the surrounding environment with through conduction. So that is energy input and another energy output. So you see, that's how open systems work. There are no boundaries upon which you have to operate. Like, you can input matter and energy into these systems, and those energy and matters can come out of the system without any restriction. And some examples of these are that ecosystems. All ecosystems are actually open systems. So there are no bars on any matter and energy input that goes in. So in a rainforest, what is the energy input? Well, sunlight. Sunlight is a huge energy input. Matter. Well, what's the matter? Rainfall. Rainfall happens all the time. And what is the output? Well, output can be matter in terms of fruits. Fruits. This can also be linked with the natural capital of a forest. So fruits, wood, these are the outputs of the system, and matter outputs. And how about the energy outputs? Well, you see, this is an indirect thing, of course, but still, if the groundwater gets all the water rainfall from the all the rainfall gets percolated into the groundwater, and after that, the trees use that water, and they get that water from their roots, and then they can produce their own ATP to produce their own food. So that's another energy exchange or output, right? So these are the examples of an open system, and this is the desert. I'm sure you can also link with these other ecosystems in the same manner as we did here. Let's move on. Closed systems. In the last open system, we saw that only matter and energy are both exchanged. However, in the closed system, only energy is exchanged. Um, Let me just read this paragraph out for you. All of these nutrient exchanges taking place on Earth are all closed systems, right? So there is only a finite amount of nitrogen in the world, right? There's only a finite matter of nitrogen. However, it keeps getting recycled, and in terms of energy, it keeps getting recycled in terms of energy. And there is no new input of nitrogen. Although I'm not sure if asteroids hitting Earth has some sort of let's say nitrogen content in them, although I think that's close to negligible. So nitrogen keeps moving around in different places in different quantities, but in different energy levels, at different energy levels. Thus only energy is exchanged in the nitrogen cycle. Same can be said for the carbon cycle, wherein only a finite amount of carbon is present on Earth. However, it keeps getting exchanged in terms of energy. Another example of a closed system can be where can be a boiling can be a boiling pot with its lid on. So in the last example, we saw a boiling pot with it without its lid. How about with its lid? Now we'll be looking at it with its lid on. So when there is a lid on this on the open system, we can see that no matter can be exchanged with the outside world, basically, because there is no evaporated water which can go out. However, heat can be felt through conduction on the surroundings of this very hot cooking pan, right, or kettle. And this one here, this is the moon. So herein the same principle follows, where only there is no matter exchange with the outside world, maybe a few asteroids here and there, but we can, in terms of an example, we can approximately say that this is a closed system, because there is no new matter which usually falls upon the moon. Only a finite amount of matter is present here. However, energy is exchanged, because otherwise the moon wouldn't be shining because of the sun's light. So that is an energy exchange. And the coffee lid, that's the same principle as here, because there is no evaporated water which comes out of the open lid. However, heat is felt through the containers, the outside container of um, the coffee, of the coffee cup, right? Okay, let's move on. Now this is very interesting. Isolated systems, matter and energy are both not exchanged, right? So this is actually a hypothetical concept. It's not practical. So if you do physics, you'll see that there are many questions wherein there is an assumption. It says here, law of conservation of momentum. In an isolated system, the total momentum remains constant. Okay, in an isolated system, the total momentum remains constant. This is a assumption, however, because we cannot have an isolated system in real life. Because so basically, in this what I want to explain through this example is the total momentum is not always conserved, because it is always lost. Some of the momentum is always lost in terms of friction, or or any other things, resistance due to resistive forces. So that is the reason why momentum is not always conserved. Thus, they have to specify that in an isolated system, the total momentum remains constant, and that is to further exemplify my point regarding it being a hypothetical concept. Now, I would like to place another food for thought, some more food for thought for you, right? Before that, since we were talking about momentum, so let's look at the collision of these two balls here. Before collision, they are moving towards each other. During collision, and due to the momentum being absolutely conserved, all of the momentum from this red ball is transferred to this blue ball and vice versa. Thus, they move in the opposite directions, and Newton's second law holds very good, right? Because this is an isolated system, and we are assuming that we are making assumptions regarding the negligible resistive forces or the momentum being conserved. Because this, and we can place this in an isolated system, right? Now, what actually is an isolated system? Now, I would like for you to try and make an isolated system. Okay. Take this very hot soup. Okay. Now, place a lid over it that stops any matter exchange. However, heat. How about heat exchange? Can you make some? Can you do something that will prevent heat from escaping this pot from in any manner? Well, I'll give you 2-3 minutes. You can think about it. You can pause the video if you wish. But what many scientists have done, they have placed the lid on top of this, and that also some very special lids, which which the lids itself, such that they don't interact with the outside world by conducting heat through the lid itself, through the outside of the lid itself. So some very special lids, and they insulate this whole bowl with very special insulating material which prevents any heat from escaping. However, any heat is impossible. A little amount of heat always escapes. So it is still a hypothetical situation. However, in some for some short instances, there have been of course attempts to make a completely isolated system. And this is a very simple type of diagram to show you how isolated, closed, and open systems work. Right? You can see here. And the best example for an isolated system that is hypothetical, and we don't know if this is true or not. However, we can say that our universe itself is an isolated system, because we don't know if there is. So we are considering that that the universe is only one universe and there is nothing outside of it. So there is only our universe. So we can assume that it is a isolated system because there is nothing outside of our universe. So whatever happens in the universe stays within the universe. So matter and energy exchanges do not take place. The applications of these are in physics, as you can see here, momentum problems, and as for chemistry, maybe when we are calculating the total energy of something using the equation Q equal to mc delta T. Therein we can assume the system is an isolated system, such as to not let any heat escape. And then there's often that follow-up question, that what are the assumptions that we've taken in this video? What in this question? What may be the actual answer? Right? So this ends our second video regarding the types of systems, and soon you will see that we have another system video with some TOK applications ready for you. Thank you. I hope you enjoyed the video.